Let's go through activity 12. So the first thing that I want you to do is to highlight the commands that define the function visualize.relationship so that we can look to see what the relationship between y and x with a partition model or a random forest actually looks like. So two ways of doing it: we can either highlight all of the lines of code that correspond to this function, or we can click on the arrow next to the name of the function and just highlight that single line. That in effect highlights the entirety of that function. And if I click run, that will go through and actually run all of the lines that are required to define that function. So I see that it's here and it's ready for me to go. All right, so for question 1, what we're going to do is we're going to look at the ex9.store database. And in this data set, what we have are shoppers' behaviors, whether or not they bought or did not buy at a bunch of different stores, just generically labeled store 1 all the way down to store 68. Now, one thing that businesses like to do is to develop customer profiles. What set of stores do customers tend to shop at? What set of stores do customers not tend to shop at? And so in this case, let's go ahead and try to develop a predictive model to see whether or not a customer buys at store 8 based on the shopping habits at other stores. So one thing we know that when we do build a predictive model, we need to reserve part of that data set to serve as the holdout sample so that we can get an honest assessment of how well our final selected model is actually performing on genuinely new data that it hasn't seen before. So we will run the first set of 4 commands here, which will set the random number seed for reproducibility, choose at random the rows from our data frame, and choose 60% of those rows to call training rows. And then we'll extract the training rows from the data frame, put that into the dataset train, and everything else we'll put into the holdout sample. So we will go ahead and put that there, and there's no need to respond to anything here. And part B asks us to go ahead and build a tree. So the way that we're going to perform this tree building procedure is to run the command build.tree. I don't actually need to save that as anything or give it a name. And the way that this works is that we just type out the command build.tree and then give the formula that we want to use. And since we want to predict whether or not a shopper buys or does not buy at store 8 from everything, we can just do twiddle dot. And we're going to be building this model on the training data. And since the estimated generalization error is found with repeated k-fold cross-validation, a random procedure, it's important to pass the additional argument seed equals 320 so that I could reproduce these results if I needed to. So if I run this, what it will do is it will grow a bigger and bigger and bigger tree, add more and more rules to that partition model, and keep track of the estimated generalization errors at each step along the way so that I can glimpse back and see where I should have stopped adding rules. So graphically what we have is the estimated generalization error of the models as I add more and more splits, more and more rules to the tree. And so I have a dotted horizontal line corresponding to the tree that had the overall lowest estimated generalization error, and the solid vertical line corresponds to the tree that would be chosen by the 1 standard deviation rule, the simpler model, whose error is no more than 1 standard deviation above the overall lowest seen. All right, so the way that we determine when we should stop building the tree is by choosing the complexity parameter of the tree, the value of CP. This basically tells us how much the tree needs to improve in order for a new rule to be added. All right, so what is the value of CP and the number of splits in the partition model with the lowest estimated generalization error? Well, that's labeled for us here. We see that there are 12 splits in that tree, and the CP is equal to just a little bit over 0.009. All right, what about the value of CP and the number of splits for the model that would be selected by the 1 standard deviation rule? Well, that's clearly labeled here, and it also has, it has 7 splits and a CP parameter of a little bit over 0.01. Notice the CP parameter of the tree with more splits is always smaller because we're allowing less of an improvement for a rule to be added to the tree. We're a little bit more stringent in how much the new rule is going to improve the tree when we use a higher value of that CP. All right, B3 asks us, does this partition model show signs of becoming overfit as the number of rules added to it gets increasingly bigger? And yes, it does, because what we see is that as we make this model increasingly more complex by adding more and more rules, more and more branches and partitions, we see that the estimated generalization error starts to get larger, 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 and larger. And in fact, by the time we make an extremely complex tree with 60 or 70 splits here, we have an error that's actually much larger than the error of the naive model, basically using no splits whatsoever and just predicting why or the whether or not someone buys or not just on the majority level. So yes, we definitely do see signs of overfitting, and we see this because the estimated generalization error progressively gets larger as the number of splits grows beyond about 12, which is where we saw where the lowest value is, and it just gets worse from there. Okay, so let's go ahead and use the tree that's suggested or picked by the one standard deviation rule. So basically, we want to build a tree whose complexity parameter is equal to this value. So what we'll do is we'll name this tree, and we'll use the function rpart to do this. We're predicting store 8 from everything on the training data, and I just add in CP of that value suggested by the one standard deviation rule. And we're going to get a summary of that tree by seeing, all right, how important is each predictor variable. And we're also going to visualize that tree by doing visualize.model. And I see that I've typoed this. I've got to put in the model that I want to be looking at. So, all right, let's go ahead and fit that tree. It takes just a split second. We can get a summary of the tree, which tells us the root mean squared error on the training data that the tree makes, a value of the AIC, and then also a list of the importance of the variables. Now, the numbers here don't mean anything in the absolute sense, but comparing the numbers is giving me some useful information. The larger the number, the more important the variable is as a predictor here. All right, so which of the 67 other stores appear to be good predictors of store 8? Well, we have a list of a bunch of stores and their importances. But one thing that we notice is that, after a while, the importance drops off really quite sharply. In fact, going from store 36 to store 62, we see the importance drops off by a factor of 2, and then it almost gets halved again, going from store 62 to store 41. So there's no hard and fast rule for picking out which ones are the important ones, which ones are the good predictors, and which ones aren't. But one thing that I do see is that there does seem to be a natural breakpoint, I would say right at about here or so. So I'm just going to go ahead and copy and paste these predictors as the important ones, because the importance measure really drops off quite a lot after considering the importance of store 36. So there is a sharp drop-off in importance between store 36 and the next important predictor. So I have made a judgment call to call the good predictors just the ones with importances bigger than 4 here. That's just a personal decision of mine. You could maybe include store 62 in your list, or maybe you might just want to include stores 13 and 17, because we do see a pretty big drop-off between this 9.5 and this 6.1 here. All right, so let's use this tree to make a prediction here. Let's visualize the tree and use it to make a prediction on whether or not a shopper is going to buy or not at store number 8. So C2 says to imagine a shopper that buys at store numbers 34 through 68 and does not buy at store numbers 1 through 33. So what would we make as a prediction for this individual? Would they shop at store 8 or would they not? Well, the way we make the prediction is start up at the very top and then just follow the rules down one by one. What you'll notice is that whenever we answer yes to the question labeled in the node, we head off to the left, and if we answer no, then we head off to the right. So the first question we ask ourselves is, okay, does this person make a purchase at store 13? Well, based on the information given to us, they do not, so we head off to the right. Do they make a purchase at store 17? No, they do not. We head off to the right. Do they make a purchase in store 22? Well, no, they do not, so we head off to the right one more time. And here we've reached a leaf, our final partition. There looks to be 113 other similar individuals in the data set that fall into this partition. And of those 113 individuals, it looks like 65.5% of them do not buy at store rate, while 34.5% of them do. So that's our answer here. We would say the probability of buying looks to be 0.345. So we predict that this individual does not buy at store 8. The probability of not buying is higher than the probability of buying here. Okay, so how many other shoppers in this data set are in that final partition? Well, it's clearly labeled here. There were a total of 113. All right, so how well does this partition model do when predicting on new individuals, individuals that it didn't see when determining the rules of the model itself? So let's get the generalization error of this model here. Generalization.error. The model we named was tree, and we're trying to make predictions on the holdout sample to get that generalization error. And we'll go ahead and run it. And we see that, all right, based on our partition model, we make 174 plus 90 total misclassifications on the holdout sample for a misclassification rate of 44% here. So the misclassification rate on the holdout sample is 44%. Now, how does this compare to the misclassification rate of the naive model? Well, the naive model, looking at the training data here, the naive model predicts everyone to just be the majority class. So regardless of the individual's characteristics, the naive model is always going to predict someone to buy. And so on the holdout sample, if we predict everyone to buy, we're going to make 265 misclassifications out of these 600 individuals in that holdout sample for a misclassification rate of 44% here. So, unfortunately, we didn't really do all that much better. The misclassification rate of our model, 174 plus 90 over 600, is at 44%, so just a little tiny bit smaller. But notice the total number of misclassifications, it's just decreased by 1. Hardly an impressive performance whatsoever. So this barely beats the misclassification rate of the naive model, which would be 265 out of 600. It makes 1 fewer misclassification, which is not very impressive here at all. So this model really isn't all that useful for predicting shoppers' behaviors on new data, and that's too bad. So do we say that the model generalizes well? Has it memorized the training data, leaving it unable to make predictions on the holdout sample? Well, maybe that's what happened here. Maybe it did too good of a job on the data it was using to build those rules, making it not able to predict on new data. And in this case, we see that the misclassification rate on the training data was actually only 33%. So my general guideline is that a model is said to generalize well if the error on the holdout sample is no more than about 25% larger than the misclassification rate on the training data. So 33 times 1.25, that gives us a number that's 25% larger, is 41.25%. So since the misclassification rate on the holdout sample is larger than this, I would actually say that this model does not generalize well. It is making a lot more errors on the holdout sample than on the training data set, indicating that it looks like we've memorized some of the quirks on the training data and the model's overfit. It's not able to generalize well to new data. So the model does not generalize well since the misclassification rate on the training set is 33%. Meaning the error has increased by a factor of, well, we can look to see what that increase was. 44 minus 33 over 33 gives us the percentage increase. So it's increased by a factor of 33% here. Bigger than the 25% guideline. So, okay, this partition model isn't that great. It didn't make predictions really all that much better than the naive model, and it's making a much larger fraction of misclassifications on new data than on the data it used to build those rules. So a pretty bad model, actually. One that I wouldn't be using to make predictions for genuinely new customers. All right, well, what about a random forest? Random forest models very often outperform all other techniques. So to build that random forest, we first need to set the seed because it's a random procedure. And I'm going to set it to 320 for reproducibility. And I'm going to name my random forest, just forest in all caps, and I'll run the command random forest. My formula is just what I want to predict, y twiddle dot in this case. I want to use all predictors. And I'm fitting this on the training data, and I'm going to fit 1,000 trees. So n tree equals 1,000. And once that's done, I'm going to obtain the generalization error. I'll go ahead and copy that. Look to see what the misclassification rate is on the holdout sample. So set the seed, make the forest, wait a few seconds for it to go, and then run generalization error. All right, so we've improved the misclassification rate now. So the misclassification rate is 40.8%, a slight improvement over the naive model and the partition model, but this is still not a very useful model here. It's making a lot of errors still. So it's an improvement, but it's still not a fantastic model. All right, well, what about regression? We've talked about logistic regression for predicting a categorical response. Maybe a logistic regression will happen to do better than these other techniques here. So what we're going to do is we're going to search for a good logistic regression model. There's so many predictors here that it would take too long to run build model. And so we're going to start out by fitting the naive model, essentially predicting store 8 from nothing, so twiddle 1. And we're going to fit that on the training data here. And we're going to turn on logistic regression by putting family equals binomial. All right, and then for the upper bound of the search, what we're going to do is we're going to fit the model with all predictors in it, but no interactions, because that's going to take way too long. So twiddle dot can be my full model, predicting store 8 from all the predictors I have available to me. And then the step command is the same that it always is. I say where I want to start, and in this case I'm going to start with the naive model, and add in variables, kick out ones that are already in the model until the AIC can no longer improve. So I have trace equals to 0 so that I'm not bothered by all the output. Oops, I forgot to run these first two commands first. And after a few seconds, it will converge to a final model where it can't improve it anymore. It can't decrease the AIC by adding in a new predictor or kicking one that's in there. And so now we can get the generalization error of the logistic regression model. Now, this wasn't built with trying to generalize in mind, but very often models with low AICs, which are relatively close to the truth, end up doing not that bad. So let's see if we use the step model selected with the stepwise search, how well that predicts on the holdout sample. And we see that the misclassification rate is 43%. So worse than the random forest model, a very slight improvement over the partition model or the naive model. None of the models we've considered are really all that impressive, unfortunately. It looks like it's just very difficult to predict whether or not someone does or does not shop at store 8 based on their shopping behaviors at these other stores. All right, so when y is a categorical variable, typically the random forest will perform the best. On your homework, you'll find actually that it doesn't, but in this case, yes, the random forest predicts the best on this holdout sample. So for this holdout sample, at least, it's the best model. Now, if we had a different holdout sample, the story might change, but that's what we saw here. All right, question 2 changes gears a bit, and it's going to think about predictive models for a customer's lifetime value. And so this is the same data set that we used last week, and so we're going to read in the lifetime value data set. It has a new name, and assuming that this file is in the same folder as my RMD file that I'm working from, this will read in just fine. And it doesn't, so all right, in this case, it looks like I'm currently in the homework 12 folder, but I want to be in the activities folder, so I'm just going to do a shortcut and say working directory to the source file location, and that'll change my working directory to whatever directory this file is in. So I'm in the activity 12 directory, so I can read this in. And now I have my data set here. So once again, when we build a predictive model, we need to siphon some of it off to serve as a holdout sample to get an honest assessment of the generalization error. So I'm going to go ahead and remove the eval equals false. And to do this, I of course have to set the seed to something for reproducibility. Choose the rows at random, and in this case 60% of the rows are going to be training, so 0.6 times the number of rows in the value data frame. Put those rows into the training set, put those other rows into the holdout sample. So we'll run these 4 commands, and let's go ahead and run build tree here to find a partition model. So build tree, once again, just works by typing out build tree, and then the formula that I need to use, what I'm trying to predict, customer LV, and then what I'm going to use to make prediction. And in this case, I'm going to use all the potential predictors, so just twiddle dot. And I'm building this on the training data, and since we estimate the generalization error with repeated k-fold cross-validation, a random procedure, I add in that seed equals 320. So I can click run, and here are my results. So what I see is as I add more and more rules to my partition model, the generalization error is estimated to get smaller and smaller and smaller. And in fact, it continues to get smaller all the way down to the maximum possible size of the tree that I'm considering. So kind of interesting that the minimum estimated generalization error came from the very most complex tree that I could think of. All right, so what is the value of the CP and the number of splits in the partition model with the lowest estimated generalization error? We have 30 splits, the maximum we could have done in this case, and that corresponds to a CP of 0, in fact. Add a rule as long as it decreases the sum of squared errors by any amount, so build it to its maximum possible extent. What about the simpler model whose error isn't that much worse, whose error is within 1 standard deviation above the overall lowest value? Well, scrolling up, we see that that corresponded to a tree with just 7 splits, and a CP parameter of a little over 0.004. So only add a new rule if that optimal rule improves the R squared of the resulting tree by at least 0.004. All right, does the partition model show signs of being overfit as the number of rules added to it gets increasingly larger? No. The estimated generalization error, in this case, continues to decrease until the maximum possible number of rules have been added to the tree. So in this case, the tree actually doesn't look like it's getting overfit. It's not really memorizing any quirks in the data. The tree continues to improve, at least in terms of estimated generalization error, as we continue to add more and more predictors into that model. All right, but let's get away with that simpler model. Let's use the model suggested by the 1 standard deviation rule. So let's fit our tree, name it tree, and use our parts, trying to predict customer LV from all the variables. And we're still using the training set, and the CP that I wanted was that value selected by the 1 standard deviation rule. So once we're done with that, we can look at a summary of the tree by doing summarize tree, and then take a look at the tree and maybe make a prediction from it by doing visualize model, visualize tree. All right, so let's fit that tree, and let's get a summary of that tree. Here's the typical error that it makes, the value of the AIC, and a list of the variable importances. And then here's what that tree looks like. All right, so which is the most important predictor of the customer's lifetime value? The one with the largest value of importance looks to be total transactions. So that makes sense. The more transactions someone has, probably the more money they've spent at the company, so no big surprise there. What's the least important predictor? And I give you a little bit of a heads up saying, hey, this is sort of a trick question. We see that the variable with the lowest number for the variable importance is gender. But if I go back and actually look at my training data, notice that married was a predictor that I allowed the tree to use, but it doesn't even show up at all. So its importance is 0. So I would say that total transactions is the most important, while married is the least important. It doesn't even show up in the list of important variables. So notice the vast difference between the most important variable here, total transactions, with this huge number for importance, and say the importance of loyalty card or gender. If I just look at the ratio between the importance of loyalty card and total transactions, and put that division sign in the correct place, I see that the importance of loyalty card is super, super duper duper tiny compared to the importance of total transactions. It really boils down to total transactions when determining the lifetime value. All right, so let's make a prediction. Imagine that we have a customer that's male, married, an income of $63,000, so an income somewhere between 60 to 75, who does not have a loyalty card. All right, if that customer's first purchase was $100, uses this store exclusively for purchasing products of this type, so wallet share is equal to 100, and has made 15 total transactions, what would we predict for his or her lifetime value? Well, it's a dude, so we know we're predicting his lifetime value. But let's just start at the top of the tree and follow the rules. So in this case, whenever the answer to the question is yes, we head off to the left, and whenever it's no, we head off to the right. So we first consider total transactions. Is it less than 7.5? No, it was 15, so we head off to the right. Now we reconsider total transactions. Is it less than 10? No, so we head off to the right again. Is the wallet share less than 87? No, we head off to the right once again. Was the first purchase amount less than 139? Well, yes, because it was 100, so we head off to the left. And so our prediction for their lifetime value is 2322 here. All right, how many other customers in this data set are inside that same final partition? Notice we have 1, 2, 3, 4, 5, 6, 7, 8 different partitions. We've clustered the customers into essentially 8 different groups. And we see that there are 26 other customers in that partition. So that 2332 or 2322 is the overall average lifetime value of those 26 customers in that partition. So there's 26. All right, how well does this model do in actually predicting new customers' lifetimes? Well, let's get the generalization error of our tree on the holdout sample. And so we see that the typical error that it makes on the holdout sample is about $257. So the generalization error, and it's saying compared to the misclassification rate of the naive model. That doesn't make any sense. So let's compare that to the RMSE of the naive model. That's really what I mean. And would we say that the model generalizes well? Actually, let's ignore this completely. I'm not even going to worry about the naive model. Do we say that this model generalizes well? Well, it does as long as the error on the holdout sample isn't too much bigger than the error on the training sample, no more than 25% larger. And in this case, we see that the root mean squared error on the holdout is just barely larger than the root mean squared on the training. 243 versus 258 here. So the RMSE on the holdout sample is basically 258. The model generalizes well since this error is only a little bit above the error on the training data, which was 243. So yeah, its error is slightly worse on new data than data it's seen before, no big surprise, but it's not that much larger. We can say it generalizes well. All right, so what about a random forest here? Random forests are usually pretty good, so let's set the seed to 320 for reproducibility. And let's fit that random forest using 1,000 trees. So let's do random forest. And in this case, we're predicting customer LV twiddle dot using all potential predictors on the training data with 1,000 trees. So we can run that, and as that is completing, we'll write out the command to get the generalization error of the random forest on the holdout sample. And we can see if we do any better than the partition model. And wow, we definitely do. That error is tremendously smaller than the error of the partition model. And so what we want is we want the RMSE on the holdout sample. Is that lower than that of the single partition model? Yes. The RMSE on the holdout is only 173 versus the 258 for the error from the single partition model. So the random forest blows this partition model out of the water, this tree right here. The random forest provides a much better predictive model. All right, what about regression? Is regression competitive in this context here? Well, using build model might take a little bit of time, so let's do ourselves a little favor and not consider any interactions. So let us run bm left arrow build model. Customer LV twiddle dot day equals train, building on the training data, set the seed so we can reproduce it, and we will set the prompt equal to false because, yes, we do want to run this command. And so this will just take a few moments. And what we see is something similar to like what we were doing with the single partition model, is that as we add in more and more variables, we don't really see the model becoming overfit. The estimated generalization error stays at about constant. And so which model should we choose? Well, let's go ahead and fit the model selected by the one standard deviation rule. Essentially the simplest model that we can get away with, whose error isn't that much larger than the overall lowest estimated generalization error that we saw. So, all right, let's fit that model. So LM customer LV twiddle, and then what are the predictors suggested by the one standard deviation rule? Well, these three right here. So we'll just separate those by plus sign since we're not worried about interactions. Estimating coefficients on the training data. Fit that model, and now let's see how well it predicts on the holdout sample. It's a pretty simple model here. Is regression at all competitive to the random forest model? Well, the generalization error is 188. So the RMSE on the holdout is 188. And what we see is that that is a little bit worse than the root mean squared error of the random forest. So on this particular holdout sample, the random forest happens to be performing the best. So on this particular holdout sample, the random forest has the lowest RMSE and is therefore the best predictive model. Now the story might change if we had a different holdout sample, but at least based on our analysis so far, the random forest does much, much better than the single partition model and noticeably better than the regression model as well. Its error is about 10% lower than the error of the regression model. All right, so the last part has us explore the command visualize relationship. So one thing we know is that the linear regression model assumes that the relationship between our y variable, customer lifetime value, and each variable is linear. And that's not necessarily the case for partition and random forest models. Random forest and partition models actually sometimes figure out that the relationship is somewhat nonlinear and take that into account in the selection of rules that it chooses. So what these commands do is it just shows you what the relationship between the customer lifetime value is and the predictor variable total transactions for a few different types of individuals. So it's basically comparing otherwise identical individuals with a particular set of characteristics. It's choosing 5 of those characteristics out at random from the training data. And it's looking to see, well, what does the relationship between the lifetime value and total transactions look like? So for the linear regression model, we know that regardless of what the characteristics are, the assumption is that the relationship is well described by a straight line. So all 5 of the individuals that it's selected as we compare them, this red line here represents 2 individuals that are identical in all other regards except for total transactions. We see the relationship is positive and it's linear. And in fact, regardless of the characteristics of the other predictors here, it's always a line with the same slope. The strength of that relationship is always the same. There's no interactions in that model, so we see that that is going to be the case. When there's no interactions, the strength of the relationship between y and our predictor variable is always the same. Well, what does that partition model think that the relationship between total transactions and lifetime value looks like? Well, looking at 5 different individuals, what we see is that there's a positive relationship the way the tree is modeling it, but it's nonlinear. Notice that it's coming in little steps like this, not quite overall a straight line. So the partition model is kind of picking up a little bit of nonlinearity potentially with that relationship. What about the random forest? How is it modeling the relationship between lifetime value and total transactions? Well, what we see is that it's kind of incorporating interactions because the shape of this relationship changes somewhat depending on what particular set of characteristics I'm focusing in on. Notice that for individuals that happen to have the same characteristics as the one examined by the red curve, it's a pretty slowly changing weakly positive relationship. But for individuals with characteristics kind of captured by the blue curve here, the strength between customer lifetime value and total transactions is a little bit stronger. And if you're an individual with represented by the green or the yellow curve, we see that the strength of the relationship is fairly weak for small numbers of transactions, but then for transactions that are 10 or more, all of a sudden we have a fairly steep segment to that relationship. So, kind of interesting, linear regression is, of course, somewhat restrictive because we're always assuming that the relationship between our y variable and our predictor variable is a straight line. Some straight line. No interactions means the strength of the relationship is always the same, so those lines are always parallel. If I did have interactions, these lines might have different slopes. And the partition model and the random forest model is a lot more general. We allow the shape of that relationship to be nonlinear, and in fact, the shape of the relationship overall may be different depending on what specific characteristics I'm honing in on. And so that's why random forests very often do perform better than linear regressions, is that it's providing a much more flexible model for kind of capturing subtle nonlinearities between predictor variables, and then also capturing automatically interactions between variables that can be difficult to pick up on in a linear regression context.